Good morning, Jeanette, Chazelle, Absedi, and Ezekiel. We'll continue our discussion about Module 8. And last time, we talked about the development of numerical integration formulas. In particular, we talked about Newton-Cotes quadrature formulas. And just to recall, ang unang dalawang klase ng numerical integration formulas na makikita natin ay mga quadrature rules. So that's what we had been doing here in Module 8 and what we will continue in Module number 9. Tapos kakaiba naman yung probabilistic approach, which is the Monte Carlo simulation, which will be on Module 10, I think, right? But essentially, when we say we have a quadrature rule, okay, sila yung mga rules na pang-approximate ng isang integral. So kung meron kang integral from a to b of f of x dx, in-approximate natin to using the sum of function values scaled by some weights. You can start from 0 to n, or you start from 1 to n plus 1, doesn't matter. Sometimes there is a scaling constant in front, but pwede naman yung masubsume inside a weight w sub I. So ganito yung itsura ng mga quadrature rules. So basically what we are doing is taking the sum of function values times some weight. So parang linear combination siya ng mga function values. And the nice thing about quadrature rules, we don't need any other information. We don't need the antiderivative of the function and so on. All we need are the actual function values times some predetermined weights. Okay? Tapos sa mga quadrature rules, nababago lang sila or nakla-classify sila by choosing how to compute the weights W sub i's. Alright? Yung una nating nakitang class ng mga quadrature rules ay yung Newton-Cotes formulas. Okay. Na ang idea behind this type of quadrature rules is that we are replacing the integrand little f by the interpolating polynomial p sub n for it. All right. So basically what we do is approximate the integral of f over the interval by the integral from a to b of the interpolating polynomial of degree no greater than n over the interval. And if you carry out the calculations carefully, you will see that this will just be the sum of function values times the integral from a to b of the Lagrange basis polynomial over the interval AB. So basically, mag-fit in siya sa framework ng quadrature rules wherein the weights for each of the function values will be the integral of the associated Lagrange basis polynomial. And then last time we took advantage also of our result from interpolation theory regarding the error associated with the interpolating polynomial. And it gave us a way on how to measure or how to create a bound for the theoretical error for the Newton-Cotes formulas. So I think doon tayo nagtapos last time, okay? So nakita natin na yung absolute difference dun sa actual and approximate for the integral is equal to or is really associated with the error bound or the error term associated with the interpolating polynomial, okay? And we illustrated it in particular, I guess kinompute natin to by hand last time, sa trapezoidal rule. Ito yung nakukuha nating theoretical error. Okay? And you will see here that the theoretical error seems to be independent of the value of h that we choose. All right? So, hindi siya nagdedepende dun sa step size na kinoconsider natin. Kasi nangyayari dito ay length of the interval, quantity cubed, all over 6, times this unknown factor, which is dependent on the second derivative, evaluated at some unknown number on the interval concerned. Okay. So ibig sabihin nakita natin dito, hindi siya nagdedepende sa h. But even so, if you have a lot of data points, all right? So kung meron kang n plus 1 data points, yung interpolating polynomial natin will be a degree n polynomial. Pag napakalaki ni n, kung maalala nyo sa interpolation theory, ibig sabihin baka yung interpolating polynomial na makuha natin ay maging subject sa Runge phenomenon. Okay? So if you will use a very high number of points in the Newton-Cotes formula, you are subjecting yourself to a blow up of the L infinity error, which happens due to the Runge phenomenon, especially that the abscissas now are designed to be equally spaced. All right? So may dalawang strategies kung paano ma-avoid yung Runge phenomenon. Number one, choose the exabytes nicely. I mean, you can choose it to be the Chebyshev nodes para mapaliit yung L infinity norm ng error. Tapos, di ba, nangyayari sa Runge phenomenon kasi lumalaki yung L infinity norm ng error. Okay? So kung pinapalit mo yung L infinity error, lumiliit yung mga oscillations ng high degree polynomial, and that we know is achieved by choosing the exabytes to be the nodes or to be the roots of the Chebyshev polynomial. But we also know another trick on how to avoid the Runge phenomenon, and that is by subdividing the interval. Okay? So ginawa natin dati sa interpolation. Meron tayong interval AB. Okay? Tapos marami raw diyang points. Okay? Halimbawa. Tapos ang ginawa natin, para ma-avoid yung Runge phenomenon, okay, para mababa lang yung degree ng interpolating function na gagamitin natin, kumuha tayo ng, sinubdivide natin yung interval AB into several pieces. So sa kaso ng piecewise linear interpolants, sa bawat subinterval determined by two consecutive abscissas, we just took the linear interpolating function dun sa unang subinterval. So it's just a straight line connecting the first point to the second point. Dun sa pangalawang interval, ganun din. Pangatlong interval, pang-apat, and so on. So mga straight lines lang sila. So ito yung nakuha nating interpolating polynomial, or piecewise linear interpolant rather. Okay? So we are pasting together low-degree polynomials to avoid the very crazy oscillations that might occur due to the Runge phenomenon. Kasi kung high-degree interpolating polynomial, pwedeng maging ganito yung itsura ng function natin. Kasi nga, polynomial siya, tapos posible mag-wiggle siya along the edges of the interpolatory interval, and that will be a big problem for numerical integration. Pero kung makikita nyo here, we posted together low-degree polynomials, tapos hindi ganon kahirap yung pag-approximate. Okay? Now, if we do so, kung piecewise linear interpolant yung gagawin natin, then our approximate for the integral will just be comprised of the sum of the areas of these trapezoids. Okay? So meron tayong mga trapezoid, depende dun sa number of interpolating number of subintervals we used. So ibig sabihin, take the area of this trapezoid, add it to the area of this trapezoid, dagdag nyo pa sa area ng trapezoid na to, and so on. Okay? Or instead of trapezoids, you could have we could have used quadratic functions on each of the subintervals. Kung ayaw nyo ng piecewise linear interpolant, pwedeng parabolic splines. Meaning, for two consecutive function values, pwedeng instead na straight line yung pang-connect natin sa kanila, pwedeng quadratic function. Okay? Na smooth din naman. Tapos madali lang siyang evaluate kasi meron ka lang ditong quadratic function ax squared plus bx plus c na kailangang i-integrate over the first subinterval, and that will give you an approximate for the area under the curve on the first subinterval. Okay? And of course, you can do it for cubic, for quartic, for quintic interpolating functions between two consecutive nodes. Pero wag na sanang lumaki yung degree kasi yun nga yung ina-avoid natin, paglaki ng degree ng interpolating function. Okay? So usually we go as far as degree 3 piecewise interpolating function, which would be your usual cubic splines. Pero beyond that, medyo hindi na siya advisable gamitin kasi na-defeat yung purpose ng paggamit ng low-degree polynomial. So if you do that strategy, what you'll get is what we call the composite Newton-Cotes quadrature rules. Composite in the sense na hinahati natin yung interval at paulit-ulit natin ina-apply yung mga basic Newton-Cotes formulas para sa kanila. Okay? Now, in this discussion, we will illustrate how to derive the composite trapezoidal and the composite Simpsons rule. So kailangan lang natin alam yung mga rules na to from last time. Na-derive na naman natin siya, so I'll just quote them here. Okay? Now, let's start with the composite trapezoidal rule. Recall that the trapezoidal rule is given by this formula. Okay? Oops. Gawin kong yellow yung highlighter. Okay? So you have half of the interval times f of a plus f of b. And then we have derived that the error term is negative b minus a cubed all over 12 times the second derivative at c. So what will happen is, hatiin ko yung interval AB into subintervals. So I'll call it, tingnan ko lang kung ano yung ginamit ko. I think I used, ito si x sub 0 pa rin. Ito si x sub n. And then, kumuha ko dito ng x1, x2, x3, and I choose them to be equally spaced. Delta x yan, delta x din ito. Or, I think I used the letter h now. So, h yung usual increment. So, h. Where h is actually given by b minus a over n. Kasi kung meron tayong n plus 1 points na gagamitin, simula kay x sub 0 hanggang kay x sub n, so meron kang n plus 1 boundary points, mag-give rise yon sa n na subintervals. So ibig sabihin, bawat interval ay maghahati-hati dun sa total length ng original interval given. So ang length ng original interval given is b minus a. So each of the subintervals will have length h equal to b minus a all over n. Tapos ito yung kunento ko kanina. So sa bawat subinterval, x sub j minus 1 hanggang x sub j, gagamitin ko si trapezoidal rule. And then I'll just appeal to the linearity of the integral operator, which will allow me to give an approximate to the actual integral over the original interval a, b as the sum of the approximations on each of the subintervals. So mangyayari ay ganito. So, appeal muna ako sa linearity ng integral. Yung interval AB, hinati-hati ko into subintervals x sub j minus 1 until x sub j. Tapos, yung sum ng mga integrals na yon ay yung magiging ay equal dun sa actual value dun sa buong original interval. Alright? Tapos, sa bawat isang integral dun sa kanan, alright? Sa bawat isang ito, gagamitin ko yung trapezoidal rule. All right, so remember the trapezoidal rule for each of these guys, all right, will just be the sum of the length of the interval. So it's going to be x sub j minus x sub j minus 1 all over 2 times function value at the left endpoint, x sub j minus 1, plus function value at x sub j. All right, yan yung sinabi no trapezoidal rule. All right, so approximately equal siya dyan. And so we have a typo. Dito, dapat plus pala yun. All right. So in-apply ko lang si trapezoidal rule sa bawat integral, and that is carried over here. Tapos kinopya ko lang yung summation. Okay? And then the error term also has the same form. Okay? Alam natin yung error term ay, nasa na nga siya? Dito sa taas. Second derivative over 2 factorial times this guy. So perhaps we can write it as negative b minus a cubed. Remember, b minus a is the length of the interval on which we applied the trapezoidal rule, all over 12 times second derivative evaluated at c. Okay? Tapos, so sa bawat application ng trapezoidal rule, ito yung error term. Okay? Meron ka negative sign, andito na siya, factored in yung negative sign dyan. Tapos, ito yung length ng bawat subinterval, x sub j minus x sub j minus 1. Yung sa na-derive nating formula, naka-cube siya. All over 12 times f double prime of c sub j. Yung c sub j ay isang unknown number on the interval x sub j minus 1 until xj. Alright? So sa bawat subinterval, ito yung error term. So para makuha natin yung error term doon sa buong interval AB, isa-sum ko lang yung mga errors sa bawat subintervals, and hence we get that summation in front. Okay? So I hope that's good so far. Okay? And then what will happen here is what? Okay. So remember x sub j minus x sub j minus 1, ito yung haba ng bawat subinterval. But remember, we say they are we assume that they are uniformly they are equally spaced. So yung haba ng bawat subinterval ay uniform. So this is just equal to h. All right? So meron kang constant na h over 2 sa labas ng summation. So we can take that out. Tapos summation na lang ng mga ito. Alright? I-expand nga natin itong summation na to. Okay? So itong summation na ito ay magiging equal sa nagsisimula siya sa j equals 1. Okay? So that means we'll have f of x sub 0 plus f of x sub 1. Yun yung first term. Plus second term ay f of x sub 1 plus f of x sub 2 all the way hanggang f of x sub n minus 1 plus f of x sub n end of term. All right? So sila yung mga nasa sum na ito. And we observe the pattern. So si f of x sub 0, siya lang naman si f of a. So natira siya dyan. Tapos, f of x sub 1, f of x plus f of x. So magkakaroon tayo ng twice f of x1 plus meron kang f of x2 rito, pero yung susunod na term dito ay f of x2 rin. So we'll have twice f of x2 and so on. Hanggang yung nandito ay f of x sub n minus 1. May isa ka pang f of x sub n minus 1. So that will give us twice of f of x sub n minus 1. Alright? Tapos nag-iisa lang yung f of x sub n. Alright? And f of x sub n is essentially equal to f of b. Alright? So that's the reason why we have this formula now. F of a plus lahat ng middle function values ay may multiplier na 2. Kaya yan yung term dyan. So si f of x1, f of x2 hanggang f of x sub n minus 1, twice siya nag-appear dun sa malaking summation sa taas. Tapos si f of b, once lamang. Okay. And this guy here, buwasan ko yung mga nakasulat sa slide. Magulo na siya. Okay. So ito ay yung approximate natin para sa integral using the composite trapezoidal rule. All right. So we simply take half of the step size times the sum of f of a, f of b, and twice all the intermediate function values. Right. And then what's the error term here? So yung error term niya ay ito. So isa-sum lang natin siya uli. Ito ay h lang. So this will become h cubed. So yung h cubed over 12 pwedeng lumabas dun sa summation. So we'll be left with the sum of values of the second derivatives at some numbers on each of the subintervals. All right? And then let's take a closer look at this guy. Okay, ano yung f double prime of c sub j? All we know is that c sub j is a number from x sub j minus 1 hanggang kay x sub j. Right? So if you do so, if you remember from the extreme value theorem, which reminds me yung mga nagwa 155 dyan, ipoprove natin mamaya sa klase yung extreme value theorem. Alright? Pero sabi ng extreme value theorem, pag meron kang continuous function sa isang closed interval, lagi kang may makukuhang maximum at saka minimum dun sa closed interval na yon. Okay? So that means there exists a number, C1 and C2, on the closed interval AB such that f of C1 is the absolute minimum and f of C2 is the absolute maximum on the actual interval AB. So ibig sabihin, lahat ng f double prime of C sub j ay mas maliit kay f double prime of C2 kasi nga si f double prime of C2 siya yung absolute maximum sa buong interval AB. And then, mas malaki naman silang lahat kay f double prime of Z1, which is the absolute minimum on the interval AB. Okay? Tapos, pagka nilagyan ko sila ng summation lahat, okay, lagyan mo yan ng sum, lagyan mo yan ng sum, lagyan mo yan ng sum, the inequality is preserved kasi nagdagdag lang tayo ng mga mas maliliit at mga mas malalaki dun sa actual value. So introducing those summations there, we'll get this inequality. Okay? Pero si f double prime of C1 ay constant lang with respect to j. Walang involved na j sa kanya. So pwede siyang lumabas, giving us f double prime of C1 times summation of 1s. And that will just give us the value n. Okay? Ganun din dun sa kanan. Alright? So maging n f double prime of C2 lang sila. And, sorry. Hindi ko pwedeng gawin yung same thing dun sa gitna. Kasi yung function f double prime ay ini-evaluate natin sa mga number na c sub j. So ibig sabihin nakadepende yung value nung mga terms sa j. So hindi ko siya pwedeng pakialaman. So that will be retained over here. But from here, I can divide both sides, or I can divide all sides by the value of n. So essentially, f double prime of c1 will be less than or equal to 1 over n, the sum of the second derivatives, and f double prime will be that will be less than or equal to f double prime of c2. Okay? Now, what we have found here is that this value over here is between the lowest and the largest function value on the interval AB. And f double prime is assumed to be continuous on the closed interval AB. Alright? Dahil continuous siya sa closed interval AB, then pwede kong gamitin yung intermediate value theorem. Alright? Na ipuprove din natin sa 155. So sabi ng intermediate value theorem, kapag meron kang continuous function, alright? Tapos sa kahit anong number, mula dun sa lowest value, say ito yung sa A, ito si B, hanggang dun sa pinakamalaking value, may makikita kang element ni domain na ang function value ay yung intermediate value na yon. So meron ka dito number C. Right? So for every number between the lowest and the highest function value on the closed interval AB, you will get an element of the interval, say C, whose function value is equal to the intermediate value, provided that the function is continuous. And so f double prime is continuous. 1 over n times the summation of f double prime of the c sub j's are between the lowest and the largest function values. So therefore, there will exist an element c of the closed interval AB whose function value under f double prime is equal to this guy. All right? Kaya masisimplify ko yung error term, instead na gumamit ng sum ng mga c sub j's, maghahanap pa ako ng c sa bawat sub-interval, pwede ko pala siyang isulat lang under a generic value, f double prime of c. Okay? And then here, so kung si f double prime of c ay equal dito, all right? So we can simplify the error term. Remember, this is the error term that we got from the expansion of the trapezoidal rule. Okay? Yung pwede ko itong isulat as what? Oh, here we can say that n f double prime of c is equal to the sum ng mga f double prime ng c sub j. Alright? So itong summation ng f double prime ng c sub j, pinalitan ko lamang ng n f double prime of c. Okay? Tapos in-expand ko, ano nga ba yung ibig sabihin ng h cubed? Remember, h cubed is b minus a over n, quantity cubed. All right? So that's how I got b minus a cubed here and a 2 cubed below. But I have an n above, so that means we'll be only left with an n squared below. So mangyayari ito ay magiging b minus a quantity cubed all over 12n squared f double prime of c. Okay? Pero now I can take the n squared at isa dun sa mga b minus a to be my h. Right? So kaya nagkaroon ng h squared, tas may natira na b minus a over 12. And of course, your f double prime of c. Okay? And this is a nicer way to express the error. Okay? So yung error natin ay ito. B minus a over 12 times h squared f double prime of c. Okay? So this is our explicit expression for the composite trapezoidal rule. And this implies that this method is of order big O of h squared. Okay? Kasi yung last term dito ay meron siyang factor in h squared involved. Okay? So tingnan nga natin yung order ng trapezoidal rule. Oh yeah, the trapezoidal rule here is also of order 2. Or actually, hindi pala clear kung order 2 siya kasi wala naman tayong h involved dito pa sa trapezoidal rule. But now we know that the composite trapezoidal rule will have order big O of h squared. Okay? So habang fresh pa yung composite trapezoidal rule, I hope the derivation is clear. Let's jump to a quick example for a moment here. Okay, bago tayo pumunta sa Simpsons rule. Okay. So in this particular problem, we were asked to estimate the value of the integral of e to the x sine x dx from 0 to pi over 4. Because siguro gusto natin i-avoid yung paggamit ng integration by parts. Okay? And then we will use this, we will approximate this using a composite trapezoidal rule using 2, 3, 4, 5, 6, and 7 equally spaced abscissas. Okay? Kasi ko-compare natin yung absolute and relative errors nila. Okay? Now, in order to get the absolute and the relative errors, we need to get the exact value of this integral for illustration purposes. Okay? So carefully performing the IBP will give us 1/2 as the exact value. Okay? Tapos, pag in-implement natin yung trapezoidal rule, kapain ko lang yung trapezoidal rule. Okay? Alright. So ito yung trapezoidal rule. Paste natin siya dyan. Ito yung gagamitin natin na rule. So, ang mangyayari dito ay, okay, kapag gumamit tayo ng dalawang points, so that means we will have only one subinterval. So basically, using 2 points, that will give us the basic trapezoidal rule. All right. So that means 2 points, isang subinterval lang, which coincides with the actual interval. So ang step size natin ay pi over 4. Okay. Tapos ito yung A value natin, ito yung B value. Kunin niyo yung function value ng e to the x sine x for them. Apply the composite trapezoidal rule, we'll get this estimate. Okay? And computing the absolute error by comparing it to 1/2 will give us this guy, and that is 21.8% error. Okay? Yun yung pag ginamit lang natin na isang point. Dalawang points. So isang subinterval lamang. Okay? Now, if we go further, so tatlong points naman yung gagamitin. So meron kang A, which will serve as your x sub 0. Meron tayong B, which will serve as our x sub 2. Tapos yung gitna nila, yun yung magiging x sub 1. Okay, kasi equally spaced yung gagamitin natin. So that means H is equal to pi over 4 minus 0 all over 2. Kasi dalawang subintervals yung mabubuo natin. So that will give us value of H around this guy. Tapos you start with A, add the step size to get the next x sub I, and then add another delta x or add another H to get the third number, and that should coincide with the value of B. So ito yung pi over 4 pa rin natin. Evaluate the function values. Plug these function values into the composite trapezoidal rule. We'll get 0.52 as our estimate. Okay? And that is good because the relative error is just around 5%. And let's see if obvious yung pagiging order h squared niya. So look at the value of h here, it's 0.78. Yung 0.39 ay kalahati ng previous h. So ibig sabihin h here was halved. Dahil nangalahati yung h, pero yung method ay order big O of h squared, alright? So kung h yon, tapos naging h over 2, pero order squared siya, so ibig sabihin yung error, dapat nabawasan by a factor of 4, or na-divide by a factor of 4. And true enough, the previous error is about 22%. Divide that by 4, we get a relative error of just about 5.41%. So apparent na kaya nating observe na siya ay order big O of h squared. Okay? Now, if you move further and use more point, we add another point, say 4 points na yung ginamit natin, step size will be pi over 4 all over 3. Kasi pag apat yung points, tatlong subintervals yung mabubuo nyo. Ito yon. Tapos mula kay 0, dagdagan mo ng h, dagdagan mo ng twice h, dagdagan mo ng thrice h hanggang makarating ka kay b, computein yung function values, i-apply yung composite trapezoidal rule, ito yung makukuha nyo, which is a lot too much, pero malapit siya sa value na actual, which is 1/2. And true enough, the error is about 2%. So ano yung nangyari dito? Well, this value of h is around what? Is around 1/3 noong original h value natin, right? Kasi mukhang ito ay around 0.25, ito ay around 0.75. So from here, the h value here is about 1/3 of the original one, pero of order big of h squared siya. So ibig sabihin, pag dinivide mo by 3 yung step size, dapat yung error madidivide by 9. And true enough, the relative error here is 2.4. If you multiply that by 9, that will be around 20%, which is around the relative error we got from the original interval. Okay, and then you can go ahead and verify the same things that we observed, but this time for using more points. And obviously from this table, we see na ang pinakamagandang approximation occurred when we use 7 subintervals sa composite trapezoidal rule. Okay? Because the error now is down to a little over half, di pala 0.5%, no? Because it's about 0.006%. So the absolute error here is of order 10 to the minus 3. Okay? So it's 3 times 10 to the minus 3, right? So we can say here that the error is of magnitude or order big O of, di pala h cube, big O of 10 to the minus 3. Ito yung size ng absolute error. Okay? So that's the composite trapezoidal for you guys. Do you have any questions about it before I shift to composite Simpsons rule? All right. So if there are no questions, then let me proceed to the composite Simpsons rule. Remember yung Simpsons rule, ang ginagawa niya ay hinahati niya yung interval sa dalawang subintervals kagad. Kasi 3 points yung ginagamit sa composite Simpsons rule. So sa bawat iteration, sa bawat gamit ng Simpsons rule, 3 dapat yung ginagamit natin na data points. So ginagamit natin yung gitna ng original interval, tapos yung 3 function values dito sa mga x's na to, sila yung ginagamit nating pang-approximate, of course, with their respective weights dun sa integral. Alright? And if you'll be careful enough, dito kasi yung error naman ay magkakaroon ng fourth derivative evaluated at psi all over 4 factorial times the integral ni omega. Pero si omega ay x minus a plus b over 2 times x minus b with respect to x over the interval ab. So if you'll be patient enough to calculate the definite integral of a cubic function, which is the product of these 3 binomials, you will get this expression here. Okay, yung makukuha niyo yung error term ay b minus a to the 5th all over 2880. Okay, and again, you have this mysterious factor, all right? So this is the fourth derivative evaluated at the number c. Okay, so medyo kakaiba yung sa composite Simpsons rule kasi sa bawat application ng Simpsons rule, kailangan natin ng isang intermediate point. So ibig sabihin, sa bawat subinterval, kailangan meron tayong additional na isang point. And that will require the number of nodes to be chosen sa composite Simpsons rule ay dapat even. Kasi nga sa bawat iteration ng Simpsons rule, hinahati na kagad natin yung interval sa 2 piraso. Okay? So kung gusto natin itong paulit-ulitin, so dapat meron laging intermediate point doon sa gitna ng 2 abscissas. They should always be chosen right away. Okay? And so that will require us to use an even number of subintervals. Sa isang application, may 2 subintervals to expect. When you want to apply the Simpsons rule twice, you will need 4 subintervals. If you will apply it thrice, you're going to need 6 subintervals. Okay? So that's why the idea here is in doing the composite Simpsons rule, we need to divide the interval AB into an even number of subintervals. Okay? So, gagawin ko siyang sulat ko yung interval AB as the interval x0 to xn, all right? And this is a closed formula, so we know that A is x sub 0 and B is x sub n, all right? Pero ang usapan, hatiin natin siya sa even number of subintervals. So, ibig sabihin si n, dapat ay even, all right? So, that's why I want to write n to be twice another integer m. And so dahil hatiin ko si interval AB sa 2m intervals, so the step size, if we will be assuming that the subintervals will be of equal length, so dapat ang h ay b minus a all over 2m, all right? And in order to get from one exabyte to another, we need to apply as many h's to a as needed. Okay? So, ganun pa rin yung nangyari. Hinati natin siya. Ngayon, ang problema nga lang, dapat even yung number of subintervals. And so again, appealing to the linearity of the integral operator, di pala linearity to, ano? So, siya pala ay paghahati, additivity pala siya ng integral operator, hindi linearity. So, yung additivity ng integral over the interval AB, ibig sabihin, pwedeng patingi-tingi kung i-evaluate yung integral sa mga mas maliliit na intervals, basta yung union ng mga subintervals na yon ay equal kay AB. So, pwede kong gawin ito. Okay? So, it would be from x sub 2j minus 2 until x sub 2j. Kasi yung boundary ng bawat subintervals na ginagamit natin ay mga even indices. Right? So, kasi ganito yung mangyayari. Meron tayong x sub 0, x sub 1, x sub 2, x sub 3, hanggang x sub 2m. Even kasi dapat yung subinterval. So sa isang application ng Simpsons rule, dapat tatlo yung points na ginagamit. Kasi dapat bawat application ng Simpsons rule, dalawa kagad yung subinterval. So hindi ako pwedeng mag-integrate mula kay x0 hanggang kay x1 lamang. Kasi isang subinterval lang yung meron ako. Unless hahatiin ko pa siya sa gitna. Pero nga, sinestematize natin yung paggamit ng Simpsons rule. So ang idea rito ay, dito ko muna siya i-evaluate. Ang una kong subinterval ay x0 hanggang x2. Alright? Para alam ko na yung intermediate point na gagamitin ko, which is x1, which turns out to be the midpoint between x0 and x2. And then you can guess that the second application of the Simpsons rule will be done on the interval x2 to x4. Tapos kailangan ko uli yung midpoint nila, namely x3, to serve as the third point in the formula. Okay? And that's why you see here that the upper and the lower limit of the integral are always even numbers. Kasi yung odd numbers, sila yung intermediate point, which is actually the midpoint between the two bounds. Okay? Kaya even dapat yung boundary rito. At kapag ka even na yung boundary dyan, pwede kong gamitin yung Simpsons rule na ngayon. So ito yung length nung subinterval kung saan ko in-apply yung basic Simpsons rule. So that will just be x2j minus x sub 2j minus 2. Sabi ng formula, divided by 6 daw yan. Yung dinerive natin last time. Tapos ito naman yung summation dyan. Okay? And then merong error term involved. Kukunin ko lang yung sum ng mga errors sa bawat subinterval. Okay? Now this guy is what? This is actually just h. Tama nga ba? Length ng bawat subinterval. Okay, that's it. 2m. Tingnan nga natin, b minus a all over 2m. I think it's 2h. Tingnan nga natin. Kasi sabi niya ang xi ay a plus ij. So ang x2j ay equals sa a plus 2j times h. Tapos si x sub 2j minus 2 ay equals sa a plus 2j minus 2 times h. When we get the difference between x sub 2j and x sub 2j minus 2, so that will be this guy minus this guy, will be left with 2h. So yung numerator pala rito ay 2h, may divisor na 6, So that will simplify to h over 3. Okay? And then we'll expand this, guys. All right? So pag in-expand natin yan, makukuha ko pala uli ay si f of a, tapos si f of b, tapos yung mga intermediate points ngayon may iba-iba na ngayong, may iba't iba na ngayong weights. So tingnan nga natin kung paano siya nangyari. Okay. So we start with j equal to 0. Kapag ka si j ay equal kay 0, yung first addend natin ay hindi pala 0 kasi si j nag-start sa 1. So kapag ka si j ay 1, we'll have f of x sub 0 plus 4 times f of x1 plus f of x2. Right? Yan yung unang term. And then when j is equal to 2, we'll get f of x2 plus f of x3. 4, f of x3 plus f of x4. And then plus f of x4 plus 4 times f of x5 plus f of x6 and so on hanggang sa dulo. All right? And let's observe the pattern. F of A is will appear only once in the summation. And again, f of x of 0 is just f of A. And hence, nag-iisa yung f of A dito. All right? And then, ilang beses mag-appear si f of x1? Never na siyang naulit. 4 times f of x1. Kaya merong 4. Tapos nandito si f of x1. Si f of x2 rito, mauulit siya dun sa susunod. Magkakaroon ng f of x2. Kaya yung mga even subscripts, nandito sila sa 2 times f of x sub 2j. Of course, except the 2 endpoints kasi makikita natin once lang sila nag-appear dun sa summation. Okay. Tapos pagka-add yung subscript, lagi siyang may 4 times, tapos never siyang nauulit. Kaya yung mga add subscripts, nandito sila sa 4 times. Lahat ng even subscripts except 0 and n, dito sila sa gitna. Kasi namumultiply sila ng 2. Nauulit sila katulad ng f of x4 and never else. Doon lang sila nangyayari. And then tuloy-tuloy yan hanggang kay f of x sub n, tapos never namang madadagdagan si f of x sub n. So that's why nagsosolo lang siya dyan. All right? And then what else? Okay, so this guy will be this would be 2h. Dun sa error term na tayo. This will be 2h. So when raised to the fifth, that will be 32h to the fifth. May 32 sa taas. May 2880 sa baba, lowest terms. Magiging 1 over 90. H to the fifth times this guy. And then again, we can apply the same appeal to the extreme value theorem and intermediate value theorem to get a nicer formula for the sum of f double prime of c sub j as j goes from 1 to n. And you will see that that error term will simplify to this guy. And that suggests that the error in the composite Simpsons rule is of order big O of h to the fourth. Okay? So ito yung ginagamit natin para sa composite Simpsons rule. Okay? Let me just copy this guy. Okay. Any questions with that? Medyo pinaspasan ko yung derivation, but I hope you followed the idea. Again, if something is not clear, you can either reread the text, nandiyan naman lahat ng explanation, or you can just send me an email or a quick chat if you have questions, all right? But I hope the derivation is clear because in the problem set, you might be asked to derive the composite rule para dun sa isa sa mga rules na nabanggit natin kanina, all right? Or nabanggit natin last time, right? Meron tayong 4 na open formulas at meron tayong 3 or 4 din na open formulas. But the derivation would be similar to what was done for the composite trapezoidal and the composite Simpsons. Okay? So if there are no questions, then let's revisit the example where we tried to avoid IBP in evaluating the integral of e to the x sine x from 0 to pi over 4. This time we're going to use composite Simpsons rule. using 3, 5, 7, and 9 points. You see here that I can only use the composite Simpsons rule if we have an odd number of points. Kasi kung meron kang n points, ibig sabihin meron tayong n minus 1 subintervals. Sabi natin sa Simpsons rule, dapat even yung number of subintervals. So that will require the number of points to be odd. For instance, if we have 3 points, we're going to have 2 subintervals. If we have 5 points, we have 4 subintervals. If we have 7 points, we'll get 6 subintervals, and so on. Okay? And true enough, if we perform the composite Simpsons rule, first with 3 points, so ibig sabihin meron tayong dalawang subintervals. So that means h will be pi over 4 over 2. Okay? And the estimate that we get applying this formula, paste ko pala yung formula ng composite Simpsons rule. Okay, ito siya. So pag in-apply natin yan dito sa f of x of 0, f of x of 1, f of x of 2, we'll get this guy. And the relative error is very low now. It's of order, the size of the absolute error is 10 to the, what, 1, 2, 3, 4. 10 to the negative 4. And here we just use 3 points. Compared natin dun sa nakuha natin sa composite trapezoidal, it took us 7 points in order to bring down the error, the absolute error, down to order 10 to the minus 3. Pero ngayon, we have an absolute error of 1 order less, 10 to the negative 4 na yung size niya, and yet 3 points lang yung ginamit natin. And we expect the approximation to become better and better as h decreases because our formula is of order big O of h to the 4th. So ibig sabihin, pagka dinivide ko yung step size h by say an integer n, madidivide yung magnitude ng error by n to the 4th. Okay? So tingnan natin kung ano yung nangyari. So kapag ka 5 points na yung ginamit ko, ibig sabihin 4 na subintervals. Meron akong x0 hanggang x of 4. Plug in ko sila dito sa formula na to, composite Simpsons. And then this is the approximation we get with absolute error of 1.62 times 10 to the negative 5. Let's see if that is or that was expected. Okay. So yung error ay nangalahati rito. Alright? So yung step size ay nangalahati. So ibig sabihin yung absolute error dapat ma-divide by 2 to the 4th. Okay? Yung step size divide by 2. Yung method ay order big O of h to the 4th. So dapat kung na-divide yung step size by 2, dapat yung absolute error madi-divide by 2 to the 4th, which is 16. Okay? And that is close because this is 2 times 10 to the negative 4 divided by 16. We'll get something close to 1.62 times 10 to the negative 5. Okay? Or roughly, pwede nyo tingnan, rough estimate lang, 2 to the 4th is 16, that's about 10. This is 2 times 10 to the negative 4 divided by 10. We get something around 2 times 10 to the negative 5. And yeah, true enough, it's about 1.62 yung absolute error pag n equals 5. Okay? And then you can go further, 7 points and 9 points, and you will see that the relative error can go down as 2.05 times 10 to the negative 6. Okay? So obviously, pinakamagandang approximate yung paggamit ng 9-point composite Simpsons rule. And that is expected because the Simpsons rule is of order h to the 4th. Meanwhile, the trapezoidal rule or the composite trapezoidal rule is of order big O of h squared. Okay? So mas mabilis bumababa yung error sa Simpsons rule kesa sa trapezoidal rule. All right? Any questions, guys? Okay, let me borrow 5 more minutes. Gusto ko lang tapusin yung module. Mabilis lang to. So, ang last part ay gusto lang nating makita na independent yung total error doon sa number of points na ginamit or dun sa step size na ginamit, because that's one particular issue about numerical integration, numerical differentiation formulas. Nakita natin last time sa numerical differentiation na kapag ka factor in natin yung round of error at yung truncation error, all right? Yung total error nagiging depende siya kay h. So alam na natin yung theoretical error nagdedepende kay h. Pero yung palang total error, specifically the error due to truncation, is also affected by the step size and in a bad way. Nagkakaroon tayo ng h sa denominator. So when we make h very, very small sa numerical differentiation, posible siya mag-fall apart pag pinagawa natin siya sa computers. Kasi when h becomes close to 0, the truncation error will blow up. Or the error due to machine calculations or machine round-offs ay magbe-blow up, causing the error to be very, very large. Kaya nga kung mapapansin nyo, or later ma-realize nyo na kakaunti ang gumagamit ng numerical differentiation sa research. Kasi napaka-unstable ng numerical differentiation, especially with respect to step size. And usually, kahit sa PDE o sa ODE, gusto natin yung mesh ay masyadong dense. Dapat maliit dapat yung value ni H. Pero pag sobrang liit na ni H, na-experience natin to sa numerical differentiation, hindi maganda yung nakukuha nating approximation due to machine errors. Okay? Now, numerical integration turns out to be independent of the value of H. Kahit paliitin natin ng paliitin si H, hindi lumalaki yung error masyado. So hindi siya nagbe-blow up katulad ng pag-blow up ng numerical differentiation. That's why when given a choice of using numerical differentiation or numerical integration to solve real-world problems, usually pinipili ng mga mathematicians or applied mathematicians yung numerical integration. Halimbawa kami, nagsosolve kami ng nagmo-model kami ng propagation ng sound at saka electromagnetic waves. So it's a wave equation. It's a partial differential equation. Now, if you took 151 or 152, makikita nyo na merong numerical technique, ang tawag ay finite element o finite difference method, pero naka-ankla siya sa numerical differentiation schemes. However, sa aming inverse problems, gusto namin yung step size ay napakaliit. Kaya ina-avoid namin as much as possible yung numerical differentiation. Kaya yung differential equations, okay, tinatranslate namin sa weak form, ginagawa namin siyang integral equations. Kasi mas madaling magpa-compute ng integrals or mas safe magpa-compute ng integrals sa computers numerically instead of asking them to compute derivatives numerically. Okay? So makita natin bakit hindi nakadepende sa step size yung total error. Okay. Tingnan natin halimbawa sa composite trapezoidal rule. So instead of the actual function value, ang nakakapture lamang ng computer ay yung first few decimal digits ni f of xj. So instead of the actual value, ang ginagamit ni computer sa calculations ay si f hat of x sub j after some truncation. Okay? So natanggal na yung mga sobrang decimal digits. So f of x sub j can be written as f hat plus some round off error e sub j. Okay? Tapos ito lang yung kinukuha ni computer, so nababaliwala yung e sub j. Tapos pag pinlogin natin to dun sa composite trapezoidal rule, again, gusto natin f of a, pero hindi kaya ni computer yung f of a. Ang nako-compute niya lang ay si f hat of a. Tapos, ang alam ko si f ay equals sa f hat plus e sub j. So kaya magkakaroon ako ng e sub 0 rito. Sa bawat f hat of x sub j, may associated truncation error na e sub j and so on. Okay. Tapos ito yung error due to machine round-offs or truncation error. or round-off error. So you can call it as the round-off error. Okay? Tapos ito naman yung theoretical error. Okay, now if we will assume that each of the E sub j's is bounded by the machine epsilon, okay? So mapapalitan to ng epsilon, mapapalitan to ng epsilon, mapapalitan to ng epsilon. So we'll have epsilon plus twice sum ng mga epsilon. So ito ay epsilon plus twice sum ng ilan? N minus 2, tama ba? Sorry, sum ng n minus 1 ng mga epsilon plus epsilon. So then factor out epsilon, we'll get 1 plus twice n minus 1 plus 1. Nasa labas yung multiplier na epsilon times h over 2. Okay? Now, if we sum this up, we'll get what? We'll get, this guy will be 2n minus 2 there. Makakancel yon. So we'll get, yung 2 makakancel. So matitira lamang ay h times n times epsilon. Okay? But n times h is basically your b minus a, right? So kasi ang h ay b minus a over n, multiply both sides by n, so we'll get b minus a. So essentially, the truncation error or the round-off error is bounded above by the length of the interval itself times epsilon. So hindi siya nakabase kay h. So it doesn't matter if we subdivide the interval into 1,000 pieces. Kasi yung total round-off error ay nakadepende lang dun sa length ng totoong interval times the machine epsilon. So it doesn't matter how small h is, it doesn't factor into the calculation of the round-off error. So basically, the round-off error is always bounded above by the length of the interval times the machine epsilon. Okay? And so it doesn't suffer from the same instability issues like numerical differentiation formulas kapag ka lumiliit yung value ni h. All right? So kaya mas magandang gamitin in a machine ang numerical integration techniques kesa sa numerical differentiation techniques. Okay? And I think that ends module number 8. Guys, you have a questions? Oh, you have questions? You have a questions. Halatang kailangan ng kumain ng lunch. So questions, guys? Andyan pa ba kayo? I hope everything is clear kahit feeling ko medyo mabilis. Okay, so I'll take your silence as no questions, okay? So with that, you are equipped to answer lab exercise 5.1. So this is worth 25 points kasi kalahati lang siya ng exer 5. Tingnan natin kung anong pinagawa. Sino nga bang gumawa nito? Sige, wag ko na lang i-reveal. Baka i-bash niyo yung sumulat nito kung sino sa mga lab instructors. But here, you were asked to derive the Boole's rule. Parang binigay ko lang siya sa work text, dun sa module. So just write down the derivation for it. And then you will need to apply Boole's rule in order to evaluate or to approximate this integral. Hindi pala required na Boole's rule yung gamitin sa number 2. Because alam mo yung points negative 2, 8, negative 1, 0, 1, 4, 1, 2, 5. Tapos, totoo siya sa lahat ng integers, x e to the power x. Using an appropriate Newton-Cotes quadrature rule, utilizing all the given data in the problem. So ano yung mga given data in the problem? So given yung value kapag ka negative 2, negative 1, 1/4, tapos sa lahat ng integers, ito raw yung value niya para sa lahat ng positive integers. So you know that this will also be added, or this should be added to your data point. 1e, 2e squared, 3e squared, hanggang 7e to the 7. So try to figure out what type of Newton-Cotes quadrature rule will you need. Definitely that will be beyond the formulas that we have derived in class kasi ang pinakamaraming points yata natin kinonsider ay 3/8 rule. Tapos ilang points lang ba sa 3/8 rule? So kung sa Bull's rule ay 1, 2, 3, 4, 5, I think 6 sa 3/8 rule. So pero dito mukhang mas marami yung kailangan yung gamitin. Ilan? 1, 2, 3, tapos 7. So 10 points yung gagamitin nyo. So ang sinabi lang naman Newton cotes. Remember what is meant by being a Newton cote formula. Okay, paano nyo siya gagawin yung integration. Okay? So pag-isipan nyo yon, and that will be exercise 5.1. Which will be due on Monday. All right? Any other questions or clarifications, guys? Sorry, I'm 1 minute over time. But if there are no questions, then thank you guys for joining me today. Enjoy the rest of the afternoon, and then let's see each other again on Tuesday next week. Bye, guys.
Bye, sir. Thank you po.
All right.